All right, hello everyone. Today is our class number 10. We are going over our first classification model, which is called logistic regression. Okay, logistic regression is a regression model that is mostly used for classification. What does that mean? So it's a regression model. So what does that mean that we are using it for classification? Any idea? Think of the target variable. What is the target variable in logistic regression? These are probabilities. So we are talking about regression, right? So logistic regression is a regression model. So the target variables are probabilities. So at the end of the day, the logistic regression is going to tell you that, okay, if X is this, then the probability of this observation, for example, is pass or fail, is this number, 80%, 50%, 70%. So the outputs are probabilities, right? So at the end of the day, let's say this is our logistic, let me use blue. Okay, so this is our logistic regression model. At the end of the day, we're going to make some predictions. These predictions are the probabilities. For example, the probability of this, for example, this is balance. Imagine we're talking about balance versus default, right? This is the probability of default. It says that if the balance, monthly balance of a card holder, let's say, credit card holder, if the monthly balance is higher, the probability of defaulting is going to be higher, right? Makes sense. So let's say the probability is 80%. And for this one, if the monthly balance is small, let's say the probability of default is 30%. So the outcome of the logistic regression are probabilities, right? These are continuous numbers, probabilities. Then we are going to use logistic regression as a classifier. What does it mean? It means that we have to define a threshold, and based on that threshold, you can classify things, right? Now, let's say by default, the threshold is 50%. I'm going to say that if anything, if the outputs, the probabilities are greater than 50%, classify them as default, 1, or black here in this example. If they're less than 50%, classify them as non-default, right? So then so this is, guys, I want you to realize that the output of the logistic regression are probabilities. Then we can use it as a classifier depending on that threshold. Let's show that threshold is withdrawal, right? Depending on what is this threshold, we come up with two different classes, right? So for example, the black ones are the default ones, the white ones are non-default ones, okay? So remember, logistic regression is a regression model, but we are using it as a classifier based on the threshold that we define, okay? All right, so in terms of roadmap, where we are in the supervised part. So we covered a couple of models in the regression. We talked about linear regression model, polynomial models, and then penalized regression models, ridge, lasso, and ridge regression. Now we're going to cover classification models. So the first and most intuitive classification model that we use is called logistic regression. Logistic regression is part of that interpretable machine learning. Do you remember we talked about interpretable machine learning? So it means that you can perfectly interpret that. However, our goal is not to necessarily interpret the coefficients. Our goal is to come up with a better predictor, better, in this case, better classifier. At the end of the day, give me some values of X, and then I have a model, and I tell you that if that's an observation with those features belong to class A or B, default or not default, spam, not spam, fail, pass, buy, sell, hold. Does that make sense? So this is what the logistic regression is going to do. Later on, we're going to work with KNN, SVR, and et cetera. So for now, let's focus on our first model in classification. Okay, so what are the topics that we cover here? Basically, we're going to start with linear probability model versus logistic regression, right? So we're going to see that what is the most basic model that we can use to think of it as a classifier and using linear regression model. We call it linear probability model. Then we will see that that model has some caveats. You know, we have to do some transformation to fix the problem of that linear probability model. And those transformations, we're going to use sigmoid function. So sigmoid is a mapping, is a transformation that's going to fix the problem of that linear probability model for us. Then with that, we see that the logistic regression is using the sigmoid function as a mapping function to come up with predictions, right? In the second part, because now that we have a classification model on hand, namely called logistic regression, we're going to talk about the performance metrics. of the classifications, right? If it is regression, I think the performance metrics are pretty straightforward. MSE, RMSE, that's it. Any kind of regression model. But for classification, it's a little bit more tricky because the number of metrics that you can work with is more than 2, right? It's easily 10 or 15, depending on what context you're talking about. But at the heart of all those metrics that you come up with, let's say accuracy, precision, recall, FIscore, ROC or AUC, or even precision recall curve. At the heart of all those things, there is this thing called confusion matrix. And here's an example of confusion matrix for 2 classes. So I can have confusion matrix for 3 class, 4 class, and etc., right? But logistic, so this is what I want you to remember. Logistic regression is mostly used for classification when you have 2 classes. If you have multiple classes, let's say 3, 4, there are other models that we know that they're going to work better than logistic regression. However, you can do something called multinomial logit or multiple logistic regression, which is basically, at the end of the day, is going to break down 4 classes into combination of binary classes, right? So let's say you have buy, sell, hold, 3 different classes, right? If you can do it with use logistic regression, you can say buy versus rest, hold versus rest, and sell versus rest, right? So you can apply logistic regression, we call it multinomial logistic regression, to come up with classification. But practically, logistic regression is the best use when you have 2 classes. Okay, just keep that in mind. This is really important. So if you have 2 classes, this is something called confusion matrix. At the end of the day, we can summarize all the outputs in this matrix. So for example, these are on the rows we have actuals, on the columns we have predictions, right? So basically, if the actual is 1, so if a target variable actually it's 1, if someone actually failed or someone it was a default or not, right? And then we have to see what the model did, what the model said. If the model said, okay, yes, it was a default, so it's true positive, right? So true positive, it's a good number. If actually it was not default and the model said that no default, so it's also good. So these 2 numbers on diagonal are good numbers. True negatives, true positives are the one that we want to maximize them, right? And false positive, false negative, these are bad numbers. On actual, it was negative, but you predicted to be positive, so it's a false positive. Here, the actual was positive, you said it's negative, so it's a false negative, right? So these 2 numbers are bad numbers. You want to minimize them, right? But what do we mean? So again, everything can be summarized in these 4 numbers: true negative, false positive, false negative, and true positive. But what does it mean that this number is large or small? Because you want to, at the end of the day, you want to compare models with each other, you have to talk about the ratios, right? You have to come up with the statistics that take these numbers and divide them by some other number and report you back some proportions, right? Then you can come up with many other statistics in classification. For example, let's look at the row proportions, right? If I take this FP divided by row sum, it gives you something. We call it false positive rate. If I take true positive divided by column sum, so it gives me the precision. If I divide it by row sum, it gives me recall, right? So depending on how you divide these things on each other, you come up with a new statistics, right? But again, as I said, at the heart of it, there are these 4 numbers, which is called confusion matrix. Okay. Now, classification itself, whenever we have classification problem on hand, we're dealing with qualitative target variables, right? So your target variable is not continuous anymore. It's qualitative. And qualitative variables can be either nominal or ordinal. Do you remember what is nominal, what is ordinal? So can you give an example of nominal qualitative variable? Any example work. Think of any binary or multiple class variable, and then think of it if it is nominal or ordinal. Let me do it the other way around. I give you an example, you tell me if it is nominal or ordinal, right? So for example, gender, is it nominal or ordinal? It's nominal, right? It's so race, nominal, right? So for example, cats versus dog, this is nominal. However, ordinal, the ordering matters. The ordering matters, but the magnitude doesn't make any sense, right? So pass or fail, maybe you think pass is better than fail. So people can think of it as nominal as well. So maybe that's not a good example. A better example is that you're talking about GDP growth and you want to predict what are the, for example, three different scenarios down the road. High, medium, low. High is greater than medium, medium is greater than low, but the magnitude doesn't make any sense, right? So these are ordinal. So in classification, the target variable is qualitative variable, and the qualitative variables can be either nominal or ordinal. Then the qualitative variables are often referred to categoricals. Basically, at the end of the day, you will come up with a classifier that basically take the data and classify it into, let's say here, in three different categories, three different classes, right? So this is our goal based on two features. So here we have feature 1, feature 2. Tell me that, can you separate these three classes from each other or not? So that's the goal of classification, right? And again, in logistic regression, we're going to focus on two-class classification. So classification is the process of predicting categorical variables. So that's the formal definition of classification. And so this is really important. Classification problems are quite common and even more relevant, more common and relevant than regression problems. So if you think that, so in econometrics course, our hands was tied, at least for the introductory course, because we couldn't go beyond the linear probability model, but there are tons of research questions out there that the target variable is binary. The target variable is categorical. So you have to do classification. And again, it's perhaps even more relevant or common than the regression analysis. So we have to take this very seriously. Okay, so what are the examples? So for example, I don't know, in finance industry, we are talking about the target variable is financial instrumental tranches. So at the end, and the tranches are basically, pooled securities that basically you're dividing the characteristic of that security based on some features, right? So for example, you're looking at a bond, you want to say that that bond is a junk bond or investment grade bond, right? Why does that matter? So you already know that if a bond is investment grade or junk bond, but you want to use some features. You want to make some predictions. So you want to say down the road, there's this % probability that this bond is going from investment grade to junk bond. If that happens, what will happen to the price of a bond? It will decrease dramatically. What will happen to its yield? The yield is going to increase. If yield increase, the duration of the portfolio change. If the duration of the portfolio change, so you have to rebalance the portfolio. So you see how these things are really, really important in finance. So this was just one example, right? And the other examples are online transactions. So if it is fraudulent or not, loan application approved or denied. So we're going to talk about this loan application in this class, for example. Well, not the loan application, the credit card default. This is the example that we're going to work with in this class. And I think for your homework, I put one loan application or even the credit card. I don't know. I have to see one of these data sets. But you can see the application out there is huge when it comes to classification. For example, in insurance industry, when you want to price one of the, let's say the product is insurance, right? Car insurance, you want to price it. It means that you want to charge different premiums for different customers. So you have to do classifications, right? Based on customer's profile, you want to do if they're high risk, medium risk, low risk, and basically you want to charge different premiums, right? So these are some, basically just some quick examples for classification models. Now, for the rest of the slides, we're going to focus on one example from the ISLR textbook, Tipshirani Hasty. And this is a simulated data, right? It's the simulated data basically dealing with 10,000 observation. And it's very, very, very imbalanced. So when I say imbalanced, it means that only 3% of the data, the people observation in the data are going to default, and 97% are not defaulting, right? And here, this representation, so the red crosses are the one who defaults, and the blue ones are the one who did not default. And we are plotting it basically based on income and balance. It's a very, let's think of this example of a very, very low dimensional example. We only have income, balance, and either they defaulted or not, right? And for 10,000 observation, obviously, this is a subset of the ones who did not default, just for illustration purposes. And So what's the goal here? The goal is to come up with a classifier. So we want to build a classifier that performs well both in the training set and test set. So this is a goal. This is our goal. And what do I mean by classifier? The classifier can be a line or can be some nonlinear boundary. Basically tells you if the observations are to the left of this line, call it no default. If they are to the right of this line, call it default, right? And so imagine you know nothing about classification or about logistic regression, random forest, you name it. You know nothing about these models, right? If I show you this plot and I say that, okay, use your eyes and come up with a classifier. So what do? Basically, let me ask you a bunch of questions. Do you think that this is a good classifier? No, right? Because obviously there are lots of misclassification happening, right? So most probably what you're focusing on or what you're thinking of is something like this, maybe something like this. Anything to the left is going to be, let's call it not default. Anything to the right, let's call it default, right? So what we do with logistic regression is, so this is our end goal, come up with this line. This is our decision boundary, right? So we want to come up with this line. And then when I have that line, I can say, now give me a new observation. If that new observation is here, this is default. If it is here, it's not default. If it is here, it's not default. Does that make sense? Okay. And then, of course, it depends on what are the features. So for example, if you look at the box plot for balance versus default, so talking about this one, it seems that for the ones who did not default, they have lower, on average, they have lower monthly balance. This makes perfect sense, right? If your credit card monthly balance is high, so the probability of defaulting is getting higher. This is a sign that that guy is just accumulating some debt over debt and over debt. So the chances that he or she is going to default is higher. Right? So this makes sense. But when I look at the income, it's basically all around the place. It really doesn't matter if your income is low or high. And at the end of the day, there are good chances. So look at the income. There are people that default with low income and default at high income, no default low income, no default high income. So it seems that the income itself has not more, at least the power, the classification power is not as high as the balance variable here, balance feature here, right? So these are all these things that the logistic regression is going to take into account, and at the end of the day, come up with that classifier for us. Okay. So is the goal clear? The setup clear? All right. Now let's talk about logistic regression itself. As I said earlier, we're going to start with the simplest example that we can think of. I want you, in the previous example, the credit card balance, credit card default, I want you only focus on one variable, balance, versus y. The y can be either 1 or 0. If it is 1, default, 0, not default, right? Let's take expected value from both from both sides, right? I'm going to go ahead and take expected value from this line, from this function. So on the left, I have expected value of, and these are conditional expectation, right? I want to see based on different values of balance, what is the expected value of default or not default. So basically, I'm calculating something like this, expected value of y given balance, right? And we know that it's going to be equal to, basically, y is a binary variable, right? 0, 1. So if I want to open it up, so it's going to be equal to summation of yi, the conditional probabilities, right? Yi given balance. Because yi can take two values, 0, 1, if it is 0, 0 is going to cancel out the probability. So we're going to end up with the 1 part, right? So expected value of y given balance is going to be equal to expected value of default given balance. And this is literally the probability, because y is equal to 1, right? The probability of y is equal to 1 default given balance. So for short, we call it px. You can think of it probability of success, and that depends on how you define the success. Success in this case means failure. This is what you want to classify at the end of the day, right? Or in this case means default. Okay. So at the end of the day, it seems that I can, if I take expectation from the both hand side of this regression equation, I will come up with probability on the left-hand side and my simple regression model on the right-hand side. So it seems that it seems that simple regression is a perfect fit for doing this job. Is that clear? Okay. So it means that if you're on regression, you come up with probability. This is awesome, right? But What are the problems? What are the caveats? So what do you think? What are the problems of using this? By the way, we call this linear probability model. What are the problems of using this model? Can you think of what are the caveats? Let me give you a picture, maybe it helps. Look at this one. You know, the yellow dots are the true data. So for example, and we are plotting them versus balance, right? This is balance. So if the balance is higher, the true data, they defaulted. So this is default is equal to 1, probability of default. And this is probability of default is equal to 0. So actually they did not default. So in the data set, either they default or they did not default. It's not, there's not something in between, right? So if I use linear probability model, this is a fitted line. So what's wrong with this? Help me out here.
Below 0, you can't have a negative probability.
Yeah, so that's one problem, right? Ryan is saying that look at the chart. It seems that it's generating some negative numbers. Basically, if this intercept is small, because I know that balance is positive, well, it can be negative as well. It means that you have paid extra amount for your credit card. If balance is negative or the intercept is negative, so the model is generating some negative numbers, which doesn't make any sense. So then we cannot have negative probabilities. On the other hand, sometimes the linear probability model can generate some numbers greater than 1. Also, that one doesn't make any sense, right? So this is a problem. What other caveats can you think of from econometric course? Do you remember the linear probability model? There's one big disadvantage. This is a technical, more of a technical point. Disadvantage of using linear probability model. What can you think of the homoscedasticity, heteroscedasticity?
Your variance is definitionally dependent on X.
Very good, right? So by definition, the linear probability model is heteroscedastic. Because remember, the variance of the binary variable is going to be P multiplied Q, probability of success multiplied probability of failure. Okay? So multiply the n, number of trials, let's say. So by construction, linear probability model is heteroscedastic. So because of these two problems, we don't like it, right? So we have to do something about it, right? So basically focusing on the first caveat, which was that this line is going to generate some negative numbers and numbers greater than 1, we have to transform it. We have to take this line and make some change to that force the outputs, the probability to lie between 0 and 1, right? So basically we want to get something like this. This is what logistic regression is doing. It's going to transform your linear probability model in an S-curve shape sort of things. And the property, well, the good news about this new S-curve is that it's going to be restricted between 0 and 1, and it's monotone, right? So it means that you cannot, for different 2 values of X, you cannot get 1 probability. It's strictly increasing. This is important, right? It must be strictly increasing, right? So now let's think about what is that mapping or transformation that's doing the job. There are multiple transformation functions out there, like the CDF. Do you remember? If you want to plot the CDF of normal distribution, how does it look like? You remember? This is the CDF of normal distribution. Okay. Or another transformation is something that logistic regression is using. It's called Sigmoid function. Okay. So now let's talk about the Sigmoid function. So as I said earlier, we need a monotone mapping function that the range is between 0 and 1. Again, what does monotone mean? It's strictly increasing. So basically, your mapping cannot be something like this. Because if it is like this, for different values of X, it's generating the same probability. You don't like that, right? The mapping should be monotone, it's strictly increasing. And it must restrict the outputs to be between 0 and 1 because the probabilities are between 0 and 1. So if we use the sigmoid function, this is a sigmoid function, right? So the functional equation for sigmoid is, it's a function of, let's say, phi z, 1 divided by 1 plus e to the power of minus z, right? So this basically means that if z is positive infinity, what's the value of this function, sigmoid function? Just plug positive infinity to this equation. What do you get? So if z goes to infinity, positive infinity. So what do I have? 1 divided 1 plus e to the power of minus infinity. So what do I get? What is e to the power of minus infinity? 0. So 1 divided by 1, it's 1. So if z goes to infinity, I will converge to 1. Does everyone see that? If z goes to negative infinity, then what do I get? 1 divided by 1 plus e to the power of plus infinity, right? Minus, minus. So e to the power of plus infinity, infinity, 1 divided by infinity, 0. Converges to 0, right? So it's going to converge to 0. So it's guaranteed that this monotone transformation, whatever you give to it, so this z, whatever value this z can take, minus infinity, plus infinity, anything in between, it's going to be restricted between between 0 and 1, right? And this is what the logistic regression is using. So logistic regression is using sigmoid function. We call it logit in short. And basically, it's going to transform this line, linear probability model, to this line. Okay. And these are, if I want to write this equation down in more machine learning notation. So this is my function. This is my f of w and b. Do you remember? This is my f hat of x, or f of w and b. Basically, this is the function that we're trying to find. This is a function that we're trying to estimate, right? In case that we have only two classes, that function is going to narrow down to probability. We just proved it mathematically, right? And so basically, it's going to be a function of 1 divided by 1 plus e to the power of machine learning language bias plus some weights multiply features, right? And to the minus. So this is the model. This is logistic regression model. Is that clear? Okay. So let's look into. And by the way, guys, if that transformation is just as a side note, if you're using sigmoid function, we call it logit, logistic regression. If you're using CDF of normal distribution, we call it probit. Maybe you've heard this, probit model versus logit model, right? So they basically do the same job, but the transformation function is different. Okay, now let's talk about a model. So as you can see, this is, hopefully you can visualize this thing now. Basically, at the end of the day, it's going to be something like this. Something like this, right? And in a case that we have only two classes, default, not default, and etc., this f hat of x, or f of wb, is going to be our probabilities, right? Probability of success, probability of failing, probability of default, probability of spam detection, and etc. Are we good? Okay. So at the end of the day, what your logistic regression model is basically this one. So what's my goal? If I can come up with some method, if I define some loss function, or in logistic regression, we have to do something different than loss. We are not defining loss function. We are defining objective function, and we maximize that objective function. If I can do some optimization and figure out what are the optimal values for B, the bias or the constant, and W's, the weights, then you're done, right? I have a predicting machine on my hands, right? It means that I have the W's are optimized, the B stars are optimized, the B is optimized, the bias term. Now, if you give me X, I can plot that X to this equation. Everything is known. I come up with a number. That number is 80%. That number is 20%. That number is 30%. Then, so far, we call it logistic regression, and we use it as a regressor. Now, if you define a threshold, then say that threshold is 50%. If the threshold is 50%, if your predictions are greater than 50%, call it 1. Classify them as 1. If it is less than 50%, classify them as 0. So there's an extra step involved in logistic regression to become a classifier. You have to define that threshold. This is important. By default, that threshold is 50%. But we're going to talk about it. Sometimes 50% doesn't make sense, right? In many cases, it doesn't make sense. Look at this one, actually. Well, here's a good example. Someone help me out here. If the threshold is 50%, what is the model predicting? Look at the blue line. The blue line is my model, right? All no default. You see? So this is why the linear probability, this is another problem with the linear probability model, right? So it's very sensitive to threshold. You cannot do anything about it. But logistic regression is also, the outputs are also sensitive to the threshold, but it's not that severe. Does that make sense? Okay. Okay, so now, if you take this model, this is our logistic regression model, and do some mathematical gymnastic, let's say, a bit of rearrangements, right? If again, I want you to think of this f hat of x like p, call it px, and then rearrange this equation, right? So basically we have px plus px multiply e to the power of minus, let's call it z for short, is equal to 1. If you rearrange it a little more, you get to this one. So we have log of px divided by 1 minus px is equal to our linear, our linear regression model, right? Wx plus p. Does everyone see how it's gone? Again, how can I get from here to there? Basically, again, if you want, you can do it this way. So we can say, let's do p of x is equal 1 minus p of x e to the power of minus c. And that, yeah, 1 minus. Okay, so then this is our, well, I have to single it out for, let's do it that way, sorry. So I have to single it out for e to the power of minus c. So it's easier to do it that way. So I say p, for sure I write p e to the power of minus z is equal to 1 minus p, right, from here. And then e to the power of minus z is going to be 1 minus p divided by p. So e to the power of z is going to be the inverse of that. And then if I take log from both sides, natural log, so log of z, sorry, z is going to be equal, taking log, z is going to be equal to log of p divided by 1 minus p. Okay, I think that's more obvious now. Okay, how we go from that step to this step, right? Okay, so at the end of the day, we can rewrite the logistic regression model like this, the one that we have here. So this thing in parentheses is called odd. Think of it this way: the probability of success divided by probability of failure. If you're flipping a coin, what are the odds that you see ahead? We say 1, right? So because that's 50% divided by 1 minus 50%. So the odds are 1 for 1, right? So the log odd, we call it logit. And so at the end of the day, the log odd is going to be equal to our simple Wx plus p, right? So again, when you're doing this thing in Python, at the end of the day, the predictions, the coefficients that you get are basically the weights. And the way that you want to interpret them are basically if let's say x increased by 1 unit, the log odd is going to increase or decrease by w unit. Does that make sense? And then you have to, again, in machine learning, we are not super interested into the interpretation of the coefficient. At the end of the day, we're going to use it as a classifier. Okay, give me classes. Is it class 1 or 2? Is it pass or fail? All right. Logistic regression, of course, ensures that the estimates are always between 0 and 1. Okay. Are we good so far? I think with the logistic model. So we haven't talked about the optimization yet because we haven't defined the objective function. So this is the model itself, right? Now let's talk a little bit about that decision boundary. So I want you to remember that, like linear regression model, that the model was linear, but the fit could be nonlinear, like polynomial. The same story here. Logistic regression is a linear model, but the fit, which is classifier here, can be nonlinear. How does that happen? So that all depends on how you define this Wx. If, for example, if Wx is W1, let's say we have two variables, right? X1, X2. If it is W1, X1 plus W2, X2, we get something like this. Are we good? If you have some nonlinear version of those, so W1, X1 plus W2, X2 plus W3, X1 to the power of 2. Again, I'm just making up some models. It can be something like this. You can even make it more complicated, right? You can even make it more complex. Maybe I have, I don't know, x to the power of 3, x to the power of 4, and etc. x1, x2, and etc. Right? So this is more complex. And as you can see, when I go from left to right, so do you remember we talked about bias variance in regression? You have exactly the same concept in classification. So model bias, model variance. So what is the model? So think about this one. What? Give me actually these. Let me write model bias versus model variance. I want you to compare the first one with the third one. So model bias in the first one, is it higher or lower?
Number 1.
Yeah, number 1. Remember, bias on average, are you capturing the pattern of the data or not? So the bias is higher or lower here for model number 1? Lower. On average, we are not, let's say, capturing the pattern in the data, right? So the bias is lower, but the variance is higher. But here, number 3, on average, you're capturing the pattern. Look at the classifications, right? If I do, maybe if I do another sample, I get something like this, another sample like this. But it seems that on average, we're capturing, so the bias is going to be, oops, sorry. Here, the bias was high, my bad. Bias is high here, variance is low. I said, but I wrote it differently. Here, the bias is low, but the variance is high. Does everyone follow? Okay, so if I said it the other way around, well, I apologize, because this is, we know that this is a simple model, this is complex model, right? In simple model, bias is high, in complex model, bias is low. And then, do you remember we had penalized regression? You can apply all those concepts here. You can add the penalty term in logistic regression and use lasso with logistic regression. Use elastic net with logistic regression. You can combine all these things, right? I'm going to show it to you where you should put that L1 norm and L2 norm in the logistic regression model. All right, now let's talk about the engine, right? So when I write this, for example, when I write model.fit X train, Y train, what the machine is actually doing, what's happening behind the scene, right? Let's talk about that engine. So the engine in the logistic regression is maximum likelihood estimation, right? It's MLE. It's not OLS or the things that we saw in regression analysis. It's MLE. But now let's talk about what is that maximum likelihood estimator, because I received multiple comments that you didn't quite get what does this maximum likelihood estimator do. So the idea is that in logistic regression, instead of minimizing the loss function or the MSEs, you're maximizing the likelihood function. So what is this likelihood function? Likelihood function is the probability that the true numbers in, let's say, in the data are coming from the model, assuming some parameters. Let's say I have a B bias term and a W. Assuming those numbers, what is the probability that the data is coming from the function? Does that make sense? We're going to look at the visualization, which hopefully help you out understanding what is maximum likelihood estimation doing. But the likelihood function, the definition of likelihood function is basically what I just covered, right? The probability that the data is coming from a distribution given some values for parameters of that distribution, right? So I found this really interesting visualization. Let's actually go over it together. We're going to work with a very simple example, and then we're going to extend it to logistic regression, to the S-curve, right? Let's say I have 10 numbers. Oh, I cannot write on this. So let's say we have 10 numbers, right? 78, 95, 100, 100.6, 102.8, and etc. Right? These are the 10 numbers. And you're interested to basically come up with the distributions. And let's say these are originally they came from normal distribution, right? A normal distribution is completely pinned down with two numbers: average, variance, or standard deviation. Basically, your goal is to find that average and a standard deviation that maximize the probability that this data is coming from that distribution. Does that make sense? Okay, so let's actually give it a try. So imagine, well, let me actually not play around with the variance. Look at the average. Look at this 10 numbers, 78. What's the average? You know, ballpark estimate. What do you think is the average? Look at these 10 numbers and tell me, what do you think of the average? Very, very rough number. I don't want you to be precise. It should be around 100, right? 100-ish. It's not 10, right? It's not 20, right? So let's say I think that in this, I want to find the probability that these numbers are coming from this normal distribution. A normal distribution with the average of 25, the one that I'm plotting here, with the average of 25, and the variance of, let's say, what is the variance? 128. What's the probability? Do you agree that the probability is very small? The probability that those 10 numbers are coming from this normal distribution is very, very small, because the average is off, right? Now let's increase the average. As I'm increasing the average, as you can guess, the chances that these 10 points are coming from that distribution is getting higher and higher and higher. Does that make sense? Okay. So at some point, you said that 100, right? When I get to 100, it's very close, right? So it seems that now, if I come up with a way that I can calculate the joint probabilities that these 10 observations happen simultaneously, the joint probability. If I maximize that probability by changing the mu and variance in this example, this is maximum likelihood estimation, right? So guys, remember, if I somehow calculate the joint probability, so the probability of that number, so the first observation is 78, right? The probability that the data is 78 and this observation is 95, the next one is 100, 100.6, and etc. The joint probability given the parameters of the distribution, the parameters are here mu and sigma. If I can find that probability and then somehow maximize that probability, how do I maximize it? By changing the parameter. Then I come up with maximum likelihood estimation. So if I click on the answer, so the answer turns out to be 104.3 and the variance is 128.5. So as you can see, maximum likelihood estimation is a technique that by changing the parameters of the model, it's trying to maximize the probability of these green dots happening under the, let's say, whatever distribution they came from. Does that make sense? The probability of observing the data, you want to maximize the probability of the observing the data, realizing the observations in the data, given model parameters. In this case, the model parameters are two numbers, mu and variance. In logistic regression, what are those? B and W's. Does that make sense? So I ask you, can you do the same visualization with the S-curve? So look at that. What are we trying to do? At the end of the day, we are trying, so MLE is trying to find B and W's. In this case, B is B0, W is B1. So let's say we are in 2 dimension, right? So it's trying to change these two numbers. And at some point, get to it is basically maximizing the probabilities, right? Let's say, for example, this is observation A, this is observation B, right? I have a probability for either of them. Probability of A happening, probability of B happening. If I ask you what is the joint probability of seeing A and B in the data, what's your answer? These are independent observations. What is the probability of joint probability of both of them happening together? No. If the observations are independent, use your statistic knowledge. Probability of A joint B, if they're independent, what is it? Yeah. Does everyone follow? So basically, we are defining and we are doing the same job for every single observation in the data. So we call this function the likelihood function, right? So this is, let me actually, why it doesn't go to the next slide? Nope. No, let me see. Yeah. I'll discard the notation. Okay, so basically this is our likelihood function that we are trying to maximize. What is the likelihood function? Bunch of, you're multiplying bunch of probabilities. Probability of point A, point B, point C, point D. Why? Because at the end of the day, I have hundreds of those probabilities. Basically, if I multiply all them together, that's the joint probability of them happening. Does that make sense? And you want to maximize that joint probability. So this is the engine for the logistic regression. You want to maximize this joint probability. As this sign means this is a multiply operator, we call it. Basically multiply the probabilities. And you just saw that for 2 points, why we multiply them together? Because that's the joint probability. They're independent from each other, right? So you're multiplying all these probabilities, and that's the joint probability of the blue dots happening at the same time, right? And you want to maximize that one. So the objective function, oh my goodness. Oh, maybe I should Go to the next one. The objective is to come up with, it's not cooperating with me. Okay. No. The objective is going to come up with our to maximize this likelihood function. So this, instead of minimizing the loss function, in logistic regression, we are maximizing the likelihood function, right? In practice, we can maximize the log likelihood, because if I take log from both hand sides, it doesn't change the maximization, right? But on the right-hand side, I'm not dealing with multiplication. I'm just dealing with summation, because log of multiplication turns out to be summation, right? So in practice, we do log likelihood. So in practice, it is more convenient to maximize the log likelihood, because again, we don't like that, the behavior of that multiplication operator. It's easier to do, if you're doing gradient descent, it's going to be easier to work with summation rather than multiplication. This log likelihood maximization gives us W star and B star, and unfortunately, there's no closed form solution for that. Do you remember in regression analysis, we had a closed form solution if you use OLS? Here in logistic regression, there is no closed form solution. There is no mathematical solution for this optimization, right? So when there is no mathematical solution, we have to try and error, use gradient descent, or methods like that. But in practice, we don't need to be worried about these things, because for example, in Python, you just change the solver, it's going to do the job for you. But I want you to realize that there's no closed form solution for logistic regression. Okay, so at the end of the day, we are now ready to make predictions. Again, we have W star, we have B star, so we come up with some predictions, 0.7, 0.6, 0.5, and then you set your threshold, and then you make some classification out of that. Okay. By the way, by looking at the logistic regression model, is it parametric or non-parametric? Do you remember the definition of parametric versus non-parametric? If you're imposing a functional form, are we imposing a functional form here? The answer is yes, right? Definitely yes. So this is the functional form that you're imposing. You're saying that 1 divided by 1 plus e to the power of minus something, so linear combination. So definitely it's parametric, okay? And depending on how we define a probability threshold, we can classify observations. And in practice, choice of thresholds can be different depending on the problem. We're going to look at some examples. All right, so going back to our credit card balance example, this is the output that we can get out of Python, right? And by the way, this is we have the luxury of this visualization only in 2-dimensional space. Now adding colors, so 3-dimensional space. But in real world, when you're dealing with problems with hundreds of features, you cannot visualize them, right? But let's say, for the sake of argument, let's say, at the end of the day, what's the output of that model? Remember, this is the model. Probability of defaults given balance and income is equal to this thing, right? So at the end of the day, W1 is clear. I know the optimal value. I know the optimal value for B. I know the optimal value for W2. Now, if I plug income and balance for every single dot, the model is able to tell me if it is class default or not default, right? And then we can summarize all these dots. So in practice, we don't see these dots, but we can summarize them in confusion matrix, right? So let's see what is the model is doing. So the background colors are the predictions, or the model that is making those classifications, right? So and by the way, this is a test set. So if the background is green, the model is predicting 0. Or not default. If the background is red, the model is predicting 1. So this is what you see here. The predictions, the background color, the green is no default, the red is default, right? The dots themselves, these are true values. The green dots are the actual 0, the red dots are actual 1. Does everyone follow? So here, these are the dots. So I don't like. So the green one, the red one is. Let me see if I can change the color without any headache. Yep, the 0 ones are no default. The red ones are default, right?
When you say those are the actuals, are you mean those are the observations themselves?
Yeah, these are the actual. Our test set is labeled. Remember, this is supervised machine learning, right? So the test set is labeled, and then now we can come up with true negatives, true positives, and then false positive, false negative. Let's for fun look at the false positive. The false positive ones are here, right? So I have to focus on the right-hand side, the model predicting that to be default. And then I have to count the green dots. Does everyone agree? So 1, 2, 3. In actual, these observations were not defaulting, but the model predicted that they're defaulting. So these are the misclassification. So the green dots on the red shaded area are misclassification. The red dots on the green shaded area, these are misclassification, right? So these are false positives. These are false negatives. The green ones are what? Can you tell me? True negative, right? So these are true negative. What about the red on the red side? True positive. So this is our confusion matrix. Then for the rest of the, we have time, I think, barely to finish it. For the rest of the class, we're going to talk about this confusion matrix and come up with different metrics. Right now, so this is a very good example. You can see that it's very, very unbalanced or imbalanced, right? So at the end of the day, look at the actuals. In the data set, it seems that we have 1936 observations that did not default and 64 that did default. So look at that. The ratio is very, very imbalanced, right? So if I want to only focus on the good numbers, you remember on the diagonal, they were good numbers, right? So the true negatives are good, the true positives are good. If I only look at the ratio of good numbers divided by the total thing, I get a number close to 97%, 98%. Does everyone see that? So does that mean this is a good model? No. So we have to work with some other statistics as well, some metrics. So what I just calculated is called accuracy. We know that accuracy is not going to be an indicated number when the data is imbalanced like this. So for that reason, we have to go beyond accuracy. We use precision, we use recall, and we use FIscore. Are we good in terms of motivation? Okay. Now let's focus on the classification performance metrics. So confusion matrix, we're all familiar with it. And in econometric language, we call false positive type 1 error, false negative type 2 errors. I think you're familiar with that terminology, or if you want to relate it to econometric terminology. But I want you to realize that for logistic regression, we are focusing on 2 classes. So this is a confusion matrix for 2 class. But that doesn't mean that you cannot come up with a confusion matrix for multi-class. Right? So this is an example for 3 class. So you have true positives, and off diagonals are, this is, for example, false class 1, false class 3, false class 2, false class 3, false class 1, false class 2, true class 3. Does that make sense? So maybe I was a little fast. So this is false class 2, because there's no positive negative anymore. There's more than. Why I say false class 2, not false class 3? Because look at what model predicted. The model predicted 2. That prediction was false, right? So we call it false class 2. Are we good? Okay. Let's talk about accuracy, precision, recall, and FIscore. So in that example, which was imbalanced, I just told you that accuracy is not a good score. By the way, so let's go over the definitions. Maybe the most simplistic way to think of the performance metrics is accuracy, right? Give me good numbers and take good numbers divided by all numbers, right? So let's say if I have 100 observations, how many of those 100 observations are accurately predicted, right? So this is called accuracy. Accuracy is good because it incorporates all of these 4 numbers, but it's bad because if the data is imbalanced, it's misleading, right? So for that reason, we have to go beyond that. And by the way, guys, if sometimes people use error rate, what is error rate? What do you think? How can you write it in terms of accuracy? 1 minus accuracy, right? So basically these 2 numbers, the errors divided by the total, okay? All right, so error is 1 minus accuracy. Okay, so now, I don't know why my cursor gets confused sometimes. So let's see. Okay, now let's talk about precision and recall. So we know the motivation why we should go beyond accuracy, because when the data is imbalanced, it's telling us the wrong story. So there are, in machine learning, especially in econ finance, there are 2 metrics that are highly emphasized and important. This is precision and recall. So I want you to think of it this way. Precision is, maybe the easiest way that I remember is that look at your model. Out of the predictions that the model is making, what percentage is correct? Right? We call it precision. Out of the predictions that the model is making, right? So the model is calling them 1. Out of those ones that the model told they're relevant, what proportion is actually relevant? Does that make sense? Look at that, the true positives divided by true positive and false positive, because the model predicted all of them to be, again, you want to look at the precision of your model, right? You don't look at the actual data. Just focus on the model, what the model is doing. So sometimes you're interested in to see what the model is actually doing. So I say, okay, the model told me that you are going to default. Now, in actual, in real world, how many of that prediction is correct? So we call it precision. The next one is, if you look at the actuals, if you focus on the relevance one in reality, right? I'm going to say that the one that actually defaulted, what percentage were correctly predicted? Does that make sense? So these two things are very, very different from each other, right? So this is what we call recall. So again, just to reemphasize, precision, you look at your performance of the model itself. The model predicted 1, what percentage of that predictions were correct? Accuracy, the recall, from the other hand, look at the actual observations. So in actual, they defaulted. Now, from those ones that defaulted in actual, what percentage was correctly classified? Does that make sense? So this is recall. So while recall expressed the ability to find all relevant instances, right? Remember, recall is looking at the ones that actually defaulted. The precision is the proportion of the data points that the model says was relevant were actually relevant, right? So for precision, again, you focus on the accurate, well, the precision, literally the precision of your model. For recall, you look at the real data, right? What happened in reality and what part of it was correct. So this is precision versus recall. A combination of the two is FIscore. Yep, right.
What if you care more about the true negative and true positive?
We talk about it, yeah. That's the next one, right? As you can see, you can come up with different metrics. Right? So for example, at the back of your mind, you're thinking that the true positive rate and true negative rate or false positive, these are important things. So what about them? So that's the next step. But this is mostly commonly used in finance because most of the time, the classification problem that you have in finance are imbalanced. So you have to look at precision, recall, and FIscore, which take into account both of them. So let's say I tell you that the precision is 80% and recall is, let's say, only 10%, right? How do you know that this is a good model or bad model, right? So you can take the average and say, you can take a simple average and say 45%. But this 45%, again, simple average is going to do a decent job and these two numbers are close to each other. But if they're extreme, let's say precision is equal to 100%, recall is equal to 0. If I take the weighted average, I get 0.5. This is not a good indicator because the model has a recall of 0. Sometimes precision is 0, recall is 1. That's not a good indicator, right? So you're going to use harmonic mean, which is basically defined as 2 multiply PR, precision multiply recall, divided by 2. And the reason that we have to have this multiplication is that if one of them is 0, it's going to penalize it very bad, right? So as you can see, if one of them is 0, what is the FIscore? 0. So the model which has a higher FIscore is a better model, right? All right, now let's talk about ROC, receiver operating characteristic. I want you to focus on the confusion matrix. So far we divided like this, proportionate column-wise, row-wise. Now let's do the other way. So if I go ahead and look at false positives, focus on false positives and true positives, right? And I want to say that out of those actuals that are negative, they didn't default. What's the proportion of false positive? We call it false positive rate, right? So false positive rate out of those people who actually did not default, what proportion was false positive, was wrong call? We call it false positive rate. And as you can see, true positive rate is what proportion of those who actually defaulted, the prediction was correct, right? We have seen this before. We just saw that. What was the other name for that? If you look at the previous slide, they are exactly the same. Here we call it recall, right? Here we call it true positive rate. So true positive rate, recall, or sensitivity. The sensitivity and specificity, I cannot even say that. Specificity, this is the hardest English word for me. So they're rarely used in finance and econ. So in finance econ literature, people usually use precision recall. Okay, not even true positive rate, true negative rate, false positive rate, true positive rate. So this is false positive rate, and specificity. This is the last time I'm using this word, specificity. I don't know, is 1 minus false positive rate. Okay, now let's see what we can do with these two numbers. If I put the true positive rate on the vertical axis and false positive rate on the horizontal axis, so people tend to see it as recall. And in literature, in finance, people usually replace this one with precision, but the shape is going to be different. But for now, let's focus on ROC. Okay. So I have, again, I'm having true positive rate here, true positive rate, and false positive rate. Do you agree that if I change the threshold, these numbers are going to change? All of them. In our default example, if I increase the threshold instead of 50% to 90%, it's going to impact the false positives, right? If I decrease it to 10%, it's going to impact the false negatives. Right? So if I change the threshold, I can calculate all these numbers again. So the ROC curve is basically summarizing all those numbers in a curve for you. It's going to say that start from a threshold 0, tell me what is true positive rate, the false positive rate. Then increase that threshold and up to 1, let's say 100%, right? For the maximum level of threshold, calculate the true positive rate, false positive rate, and then plot them. So this is what the ROC curve is able to do that, right? Let me actually help you out. So imagine you're talking about, let's say this row is my threshold, right? Can you give me an example that, why do I need to decrease the threshold in a classification? Yep.
In this case, if we want to catch more false negatives, because we want to catch more people who are
Exactly. Well, in practical COVID test. So if the threshold in COVID test, you want to make sure that you're minimizing the false negatives, right? You don't want to tell someone that you don't want to send people out with positive COVID out there, right? You want to reduce the threshold to make sure that you're capturing all those ones. So basically, if you reduce it, so example for reducing the threshold can be maybe COVID test, right? You're interested to reducing the threshold because you want to make sure that the false negatives are minimized, right? You don't want to send out people with positive out there in the society. If I want you to focus on the confusion matrix. If I reduce the false negatives, what will happen to true positive rate? Well, sorry, yeah. If I reduce this one, what will happen to this number, true positive rate? It increases, right? Because the denominator is decreasing. So the true positive rate is increasing. So if you reduce the threshold, the true positive rate is going to increase. By construction, you did it. You shouldn't be surprised because you're playing around with that threshold, right? Now, if I increase the threshold, let me give you an example. Spam detection. In spam detection, why I'm interested in increasing the threshold instead of 50%, let's say 80%. What I'm trying to do. Yeah, I'm trying to minimize the false positives, right? Because again, imagine you're making a model, you don't want my emails to go to your spam folder, right? You want to minimize those false positives. So for that reason, you're increasing the threshold. You're increasing the threshold to reduce the false positives. And if I reduce the false positives, what will happen to false positive rate? Look at that. If I reduce the false positives, then the false positive rate, the numerator is going to shrink, and then the whole false positive rate is going to shrink. Is this clear? Okay. Now, quickly, let me walk you through about these 2 points, and then we can move on. So here, if the threshold is equal to 0, if threshold is equal to 0, what does it mean? The model is always predicting 1. Does that make sense? The threshold is 0. So the predictions are always 1. Let's say we have, I don't know, 30, 70. I'm making up some numbers, 0, 0. Does this make sense what I'm doing here? The predictions are always 1, and actuals can be 0, 1, right? This is my confusion matrix. If this is a confusion matrix, can you calculate the true positive rate and false positive rate? What is true positive rate? 70 divided by 70, 1. What is false positive rate? 30 divided by 30, 1. Does that make sense? So 1, 1 is where threshold is equal to 0, and you can check it for yourself. When threshold is equal to 1, we get to 0, 0. But look at that. If the threshold is equal to 1, basically you're telling that everything is predicting the 0, right? Because the threshold is literally nothing. Threshold is 1, and everything below that is going to be called class 0, negative. So if it is, so let's say we have, these are true ones. Let's say we have 60, 65 here, 35 here. Now go ahead and calculate the true positive rate and false positive rate. 0 divided by something 0, 0 divided by something 0. Right? So these 2 points are the extreme values, and anything in between are basically different models, right? And here, this diagonal is going to be our random classifier. If by random you're doing something, you get this line, right? And this is not quite informative. If you want to put some numbers into it, we are going to calculate the area under the ROC. So if I calculate the area under this curve, what is the area under this? What is this area? If it is 1, 1, the area is 0.5, right? So 0.5 is your benchmark. And your benchmark is, basically, this is your benchmark. When the area under the curve is 0.5. If your model is doing anything AUC greater than 0.5, it's doing better than random. If it is less than 0.5, your model is poor, very poor. So this is a very bad model, decent model, very good model. So the area under the curve should be interpreted like that. Again, basically that's, let me see. Okay, we're running out of time. We're almost done. Yeah, what's the question?
Well, which matrix was showing the perfect, what was it called? The perfect one versus the random one? Which matrix showed which thing correlated to the graph? Don't know if that makes sense. On the last slide.
Oh, I see. You want to make, so you can randomly make any predictions, right? In Python, very good question actually. We're going to do it in Python next class. Okay. I'm going to randomly call them 0 or 1. Okay, yeah, very good question. Okay, so this is area under the curve, and again, the larger this number, the better. And this is basically, I took it from Wikipedia. There are a bunch of other metrics out there, but I think if you stick to the one that we discussed in this class, you should be good, at least for econ and finance. Well, majority of the literature. I think in medical science, they are more interested in sensitivity and specificity. Can you say that? Specificity? Yeah, specificity. Yeah, that's a torture. Okay, we're done. So I can pause the recording and then I'll answer the student's question. Well, let's let the recording run. Let's do them very quickly. Question number 1: are we treating y hat is equal to 51 and y hat is equal to 99 the same in logistic regression? What's the answer? Yes and no. If the threshold is 50%, yes. If the threshold is 70%, no. Okay. Second question, does it make sense to have nonlinear decision boundary? We talk about it, Grayson. Is logistic regression useful for anything beyond probability? Yes, for classification, right? Depending on that threshold level, you use probabilities and make them classification. And then for what do ROC and AUC tell us about the prediction? So we talked about it. The larger the AUC, the better. Yeah. That's pretty much it. In next class, we're going to go over all these things in Python. Guys at home, is there any question?